Right, welcome back. Um, Now, upon a request on these questions from May June 2018, paper 1-3, question 9 here, I'll try my best to present the solutions based on my perspective here. Okay. Now, for this sequence that consists of U1, U2, U3, it is given that the first term is an 8, and then the rest of the terms is given by this relation here. And then this particular equation is true for all real R value. Prove that by mathematical inductions that this sequence un equal to 4 multiplied by 5 over 4n plus 3 is true for all positive integers n here. Okay, now let's give that a try. I'm going to let Pn be the propositions that represent this sequence n equal to 4, 5. Okay, right. Now I'm going to test out the P1. Let n equal to 1 here. Therefore, I will have 1 equal to 4. And then that basically give me an 8, which is the same as the one given. Therefore, this proposition is true for n equal to 1. Alright, now I'm going to assume that, make assumption. Assume pk, the propositions for n equal to k is true. Okay, therefore it actually represents uk and then this proposition for this sequence is true for all value of r, for all positive integer for this case, for all positive integer. Okay, and then we're going to test out the propositions for pk plus 1 here. That is basically given by this sequence uk plus 1, which is the same as 5 over 4 uk minus 3 over 4, sorry. Alright, and then we know that if we make assumption uk is true, we can substitute it here, and that would give me alright. And then from here we can actually simplify that. Alright, now shouldn't be a problem. We will be able to obtain. Now let's try here. We have 5 plus 15 over 4 minus 3 over 4, which will lead us to that is a 12 or 3. Alright, now there you have it. That is UK plus 1. Now we want to test out whether this is true or not by using this particular sequence. So I'm going to represent that when n is equal to k plus 1. Let's try that using this. We're going to substitute n equal to k plus 1 into this particular equation. Let's call this equation 1. So from this equation, we have k plus 1 and then that would typically give us a 5 over 4 k in this case, because I open up the index which is 5 over 4, so you can simplify this. become a 3. Therefore, we prove that yes, this sequence is true for when n is equal to k plus 1. Therefore, this is true. This proposition is true. Now, knowing that pk plus 1, pk plus 1 is true, implied that pk is true, right? Therefore, by using principle of mathematical inductions, knowing that n is equal to 1, oops, sorry, let me rewrite that. Knowing that P1 propositions when n is equal to 1 is true, and Pk plus 1 is true, imply that Pk is true. Therefore, we can conclude that in this case, therefore, we can conclude that un is equal to 4 phi over 4 to the power of n plus 3 is true for all n that is a positive integer. Okay, and then there you have it. I hope that is clear for the first question here. Right, alternatively, some student might want to try a different approach when you perform the inductive process for pk plus 1 here. So I'm going to present another alternative methods here. Using the same approach here, we have uk plus 1. Also starting from here, that is typically 5 over 4 uk minus 3 over 4 here. And then that will be the same as I think it's better if I factorize everything. It'll be easier. Okay, hold on, just let me work this out here. So therefore it's better I just take 1/4 of 5 uk minus 3 here, and then making assumptions that uk is true, we can substitute this. That will be 1/4 of 5 times and then that whole term is a uk term. Alright, and then from here we can do a bit of manipulation here. You will notice that if I multiply this, where I expand this, right? If I were to expand this, I should be able to get, let me try and see what am I getting at. Okay, did I miss out anything? Oh yeah, I think I made a mistake here. Hold on, I always miss out my 4 here. So there's a 5 uk, so 5 by 4, 5 by, okay, hold on, this one I better put in the bracket here. There's a 4 5 over 4k plus a 3, right, and then subtract over 3. Okay, I think that's it. We don't really need to use this section here, sorry. That is a 1/4. Right, and then there you have it. From here, you can do a bit of algebraic manipulation. Now, we can actually bring in the 5 over 4 into this, and then bring out the 4. I'm going to factorize this. We have 5 over 4. That is typically 5 over 4. Multiply with 4. And then after that, I'm going to expand this also. That will be equal to 5 over 4. That is typically 15 over 4, right? Minus of 3 over 4 here. And then eventually I will end up with a 4. I can interchange this, and then that will become 5 over 4 k plus 1. and then here I will end up with a 3 here. And then you will notice that this is exactly the same as this term when n is replaced with k plus 1. Therefore, from here we can conclude that pk plus 1 is true, implied that pk is true. Therefore, by principle of mathematical inductions, we know that P1 is true and PK is true, imply that PK is true. Therefore, I can just and PK, just let me rewrite that one more time, is true, implied that PK is true. Therefore, the sequence UN is equal to this 5 over 4 to the power n plus 3 is true for all positive value of n. Alright, now I hope that is useful. If you prefer alternative method, you can use it. If you prefer the first method that I shown to you, you can also use it. Right? We're going to move on to the second section shortly. Alright, now section 2 of this question 9 here. We have proven this sequence to be true for all n which is a positive integer. Now we need to deduce the sets of values of x for which the infinite series given as such is convergent. Now first of all, we're going to substitute all the corresponding value here. We have u1 minus 3. Okay, u1 minus 3 is basically just 4. I'm going to do it separately so that we can see what is going on. And there's typically a 1 plus a 3. And then don't forget we have to subtract that with a 3. Then that will lead us to a 4, 5 over 4. And then that is typically a 5. And then next we're going to proceed on to the second part. u2 minus a 3. And then that would actually lead us to 5 square over 4 after we simplify that. Okay, that's it. And then after that we can try out the next one, which is ur minus 3. And then that would actually lead us to 5r here. And then that will be typically 4r minus 1. Okay, that's how it looked like at this point. And then we can actually substitute all this back into this term here. And then we will get the first terms to be 5x. So this term will become 5x. And then that will become 25 over 4 x squared. And so on and so forth until we have what do we have here? 5r, 4r minus 1, x to the power of r here. Okay, and so on and so forth. Right? And then if you notice that this can be written as we can actually factorize this out. We can take out the 5x, that will give us a 1. And then we have our 5, let me see here, 5 over 4 x plus, you will notice that if you try out this term here, you would eventually end up with this, and so on and so forth, until we have like, here we take out 1, 5, so therefore it will be 1 less here. We will have a 5 over 4 r minus 1 x r minus 1. and so on and so forth. Okay, I hope that is clear at this point. Okay, now this series will converge. You notice that this is um, geometric progression. Basically, this is a geometric progression. If you were to sum up the n term, most probably the n term will be equal to now the sum. Oh, all right, no, I shouldn't be writing the sum term here. I'm just saying that if you try to sum up this geometric progression, the only conditions that need to fulfill for this series to converge. So we say that this series would converge if the common ratio, so the common ratio in this case is 5 over 4 x here, must be the magnitude of this common ratio must be less than 1 according to the conditions given by binomial expansion, right? Now therefore from here we can rewrite that as x, the modulus x will be less than 4 over 5 here, or we can write down as alright, now that will be the sets of values of x which must be satisfied for the series to converge. Right, now I hope that is clear at this point. We're going to move on to the next one shortly. Now let's take a look at the last sections of this question here. Number 3, use the result from part A that we have already proven through mathematical inductions. We need to find out the cert A and B such that it satisfies this summation here. Okay, now let's try out the sum of this using this mathematical sequence that we have already proven. That will be that can be written as un. You can see that un is particularly equal to this plus a 3, subtract off with a 3, to n. And then with a bit of simplification, we found that we have a 4, 5 to the power of, 5 over 4 to the power n. Now from here is basically up to you how you want to deal with this, but I find that the easiest way is to divide and conquer. Right. Now you can split this up as ln 4 plus the ln 5 over 4 here. Right, we can apply a bit of logarithmic rule. Basically is ln 5 to the power of 4, sorry, ln 5 over 4 to the power n. We can bring down the n using the logarithmic rule. Yeah, that's what we have. And then with a bit of arrangement, this one typically says that we are going to sum up n ln 4 n number of times. Therefore, this would become n ln 4 then basically. And then this part here, we are supposed to have ln 5 over 4 n, sum of n. You can see that there is the sum of n. Basically, it means n ln 4 plus ln 5 over 4 here. We're going to sum up 1, 2, and so on and so forth until n term. So this should look quite familiar to you guys. And then we can summarize this as n ln 4 plus, this is a, how do you call that? This is an arithmetic sequence or arithmetic series here, sorry. It's an arithmetic series with a standard formula for the sum. Therefore, we can write it down as n over n plus 1 over 2. That is the summations for the arithmetic series ln phi over 4. And then from here, we can rewrite this as n ln 4. And then there's a half here. We can bring the half back as the index. That would typically give us n plus 1 here. Ln ln 5 over 4 to the power of half, which is a square root. And then with a bit of divide and conquer again, that is my favorite strategy. We can group the like terms together. So take for instance, in this case, we can take out n. We have ln 4 plus another term, which is ln cert 5 over 2. And then plus n square ln cert 5 over 2 here. And then finally, we can simplify this term. That would actually give us, I'm going to rearrange this so that it match this particular term here. I'll rewrite that as n square ln cert 5 over 2 plus n ln, after you simplify this, you will end up with 2 cert 5. No doubt that is very clear and straightforward. And then there you have it. The value for A, I can finalize that as, in this case, the A is a cert, certs A. Find the certs A. So the cert A will be cert 5 over 2. It is a cert. And then a B itself is also another cert. That is 2 cert 5. And then there you have it, right? Now I hope that is clear in this case. And then best of luck in your exam again, right? Okay, until I see you guys again, take care.